We will begin the afternoon session. As we said this morning, Professor Fabio González from National University of Colombia has the first talk, and with this very appealing season, multimodal deep learning, working with this approach in the last many years too, and we will see the last works and mainly your thought about what with this kind of things we should do. This is the challenge. 40 minutes.
Okay, perfect.
Okay. So yeah, thank you, Tiberio, and the other professors from Uniandes for the invitation and for the effort of organizing this kind of events that that allow us to meet at least every year and get an update of what everybody's doing. Okay, so what I want to talk about today is some problems that we have been researching for the last almost 10 years, which is multimodal learning, and this is like the last approach that we have followed using the trendy technique, which is deep learning and neural networks. Okay, so okay, first of all, just a quick summary of what we do in our research lab, my lab, the Machine Learning Perception and Discovery Lab at the National University of Colombia. So it's our main focus is machine learning, but we work on some particular problems which are like the main interest for us: multimodal learning, large scale learning, and representation learning. Those are like the main topics which are like common to the different kinds of things that we do. Obviously, this is motivated by real applications, but real world applications such as information retrieval, problems in computer vision, biomedical information. Also is an area we had worked a lot, and recently working in other types of data such as tests and this kind of, in general, the kind of data we work on is independent of the method, so we are always looking for like new areas where we can apply our method. So traditionally we have worked a lot on kernel methods, supported machines, and other kind of kernel methods, matrix factorization as well. But recently, okay, not that recently, since the last 5 years, we have been working on deep learning, like taking advantage of this new wave of popularity of neural networks. And obviously, to work on this kind of techniques, you really need nowadays to use some kind of technology that speed up the application of your algorithms. So we have worked a lot on distributed computing, and recently learning on the GPU processing as well. So this is like a broad view of what we do in our research lab. So multimodality has been like a topic that we have been working and revisiting during the last years. So what's the problem of the motivation of multimodality? Really motivation is that we perceive using different kind of sensors. So perception is definitely something which is multimodal, and this is a very good example. So let's see if this works. Okay, so I have to mute this one, right? One. Yeah, there you go. Okay, so yeah, the interesting thing here is that depending on what you are seeing, what you perceive is different, even though the sound signal is the same. So really, listening is also, or listening to someone is also something that involves vision, which is in some way surprising, and that's why when you look at and yeah, please later look for it, but Gork effect. And yeah, you will notice that definitely if you look at this picture or you look at this picture, your perception is going to be different when you're listening, okay? So that's multimodality, the fact that our perception involves different kinds of information. So these are different kinds of modalities, but I mean, there are as many as you can imagine, but these are typically ones, for instance, language, written, spoken, visual, images, videos, auditory information, touch, smell, taste. If you go to a particular domain, for instance, like the medical domain, you have X-rays, histological slides, biomedical signal, ECG, EEG, etc., etc. So data in general is multimodal, okay? So, oh yeah, these are more examples. So, multimodality, for instance, the news, okay, or social media. Yeah, in Twitter, you have text, but also you have images, videos, sounds, or in other places where probably it's not that clear that you are dealing with multimodal data. But for instance, this is a Stack Overflow. Probably, yeah, most of you probably know it. You go looking for answers to technical problems, okay? And typically in a Stack Overflow, you have tests, natural language, but also you have programs. So even though both are tests, they are different kind of tests because a program has like some particularity. So this is also an example of multimodal data. Okay? Okay. Yeah, in medical images, etc. So how this has been addressed traditionally. So traditionally, in the machine learning, artificial intelligence, each kind of modality has like a particular field that work with it. So, for instance, with visual information, we have computer vision. For text, we have natural language processing or understanding. And traditionally, the kind of techniques or the kind of methods that you use for processing this kind of information were very different. So the features that were developed for processing images, the features for processing tests were very different. It was very difficult to use what you did in one area and use for the other area. So, and it has to do with these kind of problems. First, the statistical properties of each kind of modality are different. That obviously nowadays with neural networks start to change because you can like use the same kind of approach for different data. However, still you can see that people that were seeing images or videos don't work with the tests. But yeah, it has to do with that the fact that those are very different areas. Okay. Yeah, the other thing is, okay, you have both, for instance, tests and images, so how do you combine them? So also it's not clear how you can mix because of the different nature. And also there are different tasks and the problem you may have with tests is very different to the problem you may have with images or you may have with other kind of modalities, medical images or things like that, okay? And in addition, you have to deal with the problem of very big collections and things like that, okay? So multimodal learning is basically the problem of how to deal with that, with different kind of data when you are trying to solve a task using machine learning, okay? So we have been working on this for a while. This is a work from 2012. And this is like the way that we used to approach that problem at that time. So, I mean, it was published in 2012, but we have been working on that like 2009 or something like that. And yeah, at that time, when we were working on this, neural networks just were like starting to be popular, but they were not mainstream yet. That will happen 1 or 2 years after the publication of this. So this was very standard way of working with, for instance, with images. So what we did at that time to work with text and with images was to use something which was called visual backward works. And it was like a similar idea to what you use for text, that you represent a text depending on the words that you have in the text and the frequencies of this is called a backward words. So for images, you have to do like a build a vocabulary, which in this case are like small patches, and then you look for the frequency of those patches in an image, so you represent that as a histogram of those visual words. So what we did at that time was to use that kind of representation for text and images, and then do something which is called matrix factorization. So we have like the visual representation, the textual representation, and then our problem of finding correlations between the visual and the text part was solved using a matrix factorization, basically. What kind of problems? Different problems. For instance, you have an image and then you want to annotate the image according to find words that are related to the image, or you can do also information retrieval, like you have images and text in your documents, and then you have a query which is only an image, and then you want to retrieve the text or the documents which are related to the image. So we use this for that kind of representation. Okay, so that was like the traditional way to deal with this kind of problems. At that time, multimodality was not really a mainstream topic. So some people were working on that, but it was not like a mainstream topic because really people working on the computer vision, it was very difficult that they deal with the natural language processing and the other way around. Okay, so yeah, deep learning came. Yeah, you already know. I don't have to talk about this because nowadays this is really popular. So basically neural networks with many layers, with millions of parameters that are efficiently trained using GPUs with millions of data. So that's basically deep learning, and this was a revolution in computer vision and in other areas such as speech analysis, natural language processing, etc., etc. So this definitely changed the way we did things before. So yeah, and it has to do with the models, okay? That every time the models were bigger and bigger and bigger. So having like a neural network with hundreds of layers is not uncommon nowadays. And then solving some tasks, for instance, this is object recognition tasks, the popular one, because this was the task where in 2012 neural network was able to beat traditional methods. Now traditional methods are called shallow, okay, contrast with deep. So yeah, that was the performance of the neural network. So everybody started to look at neural networks, and this has happened. I mean, the error has gone down, and yeah, and you can see the same for other kind of problems in computer vision and other areas. Okay, so yeah, this is deep learning, and it's very engineering thing. Really, there has not been like a fundamental discovery, because it's basically the same neural network that we used in the 90s, 80s, okay? The difference is the way that they are implemented and the resources that we have nowadays, the amount of data we have, the computer power that we have. Also, yeah, there is a change on the approach, which is something that traditionally you do by hand. That was the feature extraction, you learn that. But more than that, really is just the same algorithms and some tricks, and many tricks actually. Okay, but this recipe works very well, very well in different areas. At that time, we were working with also, in addition to the multimodal team, we also were working, yeah, for some years in analysis of medical images, in particular histopathology images. So this is a paper that we published in 2013, where basically what we did was, okay, let's take these learning models that are working very well with natural images and see how they work with the image that we used to work. And yeah, MICA is the most important conference on medical imaging, and every year they publish hundreds of papers, maybe around 500, something like that. That year, there were 6 papers on deep learning applied to different kinds of images. One of those 6 papers was ours, this one, where we applied to some kind of histopathology images for basal cell carcinoma diagnosis. And nowadays, if you look at medical imaging conferences, you have more than half of the papers, and probably even 80% of the papers use in some way or another deep learning. Okay, so deep learning became mainstream. So we were lucky, really, I have to confess. I mean, we didn't plan to, I mean, we didn't know that was going to become that popular. So we were really lucky at that time. And yeah, because definitely this work, and yeah, we got a lot of citations of that, but it was just a matter of being lucky. Nothing that, and yeah, all of that, yeah, applying this same recipe, well, we have published some papers and even get some patents, but it's the same thing. It's you have a lot of data, you have neural networks, in this case, convolutional neural networks that you apply to a particular problem, and yeah, that's and yeah, that works pretty well. Okay, so something that we were thinking about was how to involve that multimodal thing in deep learning. So there were not many works trying to do this. Like, yeah, a lot of work on deep learning for images, for video, for tests, but individually. So, however, there are some works on that. So this is a work from 2011, and this is like something which is called autoencoder. Okay, so they have an audio input, a video input, and actually the problem they were addressing with this kind of model was the same problem the video, the McGurk effect. So they show the visual information, the guy pronouncing gaga and the guy pronouncing baba, and they see how it performs when they show only the visual information, the audio information, and both using this model, this multimodal model, and in fact what they get is that the model performs better when you have multimodal information. So that's interesting. Okay. Another example of multimodal models. These are models for language, but that involve also images. So in a language model, it's like a generative model for generating text. So there are different words that involve also visual information, and that improves the text generation. Actually, one of the popular, and they have nice things such as this, like they have like some representation for images, some representations for text, and they can do things like this, like you have the representation for a blue car, and then you subtract blue, the concept blue, the word blue, and you add red, and then you get something like this. So that's interesting, that kind of things. But probably the most popular application is image caption that you probably have seen, and is to give an image and then to get a caption of the image, something like this, like a person riding a motorcycle on the road. So that's a pretty good description of this image. And in general, these kind of models work very well. Sometimes, and there are something like this, like you have like a typical model for image classification. You use that to represent your image, and then you feed that to a typical model for text generation that use recurrent neural networks. And playing with the way you connect these kind of models, you can get the model to work to generate description for the images. Sometimes it doesn't work that well. So for instance, in this case, the caption for this image, which is no parking sign, is a refrigerator filled with lots of food and drinks. So sometimes it doesn't work well, but in general, this works pretty well. Actually, you can do it in there are online services where you can try that. So I was looking for an image of National University to show in a class, and I found these kind of things that you eventually see in National University. I really don't know what the donkey was doing there in Plaza Che, but okay, I found it interesting. Actually, what I was expecting was the model to say that there was a face here or something like that. Okay, but this is what the model produces. Okay, it says, I think it's a horse standing in front of a building, and he seems okay. Okay, so yeah, that's good. I mean, that works. Yeah, and typically what happened, how the model is able to do this kind of prediction is because actually these are massive data sets, many examples, and definitely there was probably a horse somewhere, and somebody wrote a description probably very similar to this, and the model is able to to connect this with the examples which are previously there. So yeah, image capturing is something that has advanced a lot. However, what we were trying to do was a little bit different. So because if you see the representation of the images and then the test, really you are not using like the two evidences to solve a problem. You are like trying to translate from one modality to another modality. So we were trying to do something different, something more like a principled approach. So this is what we did. So the motivation of what we did is this very a synthetic example. Imagine you have a robot and it has two kind of sensors, a camera and a microphone, okay? But eventually you may get noise to one of the channels or one of the sensors. So for instance, here there is just noise in the camera, but here you may listen clearly to a dog barking, okay? And or eventually here you may listen to a cat, okay? So the problem here is how to know when you are receiving like information. For instance, here you are not receiving any kind of information in the mic, but you have your camera working, so you can again classify this as a cat or the same thing with a dog. Okay, so it's a scenario where you have like multimodal perception, but eventually you may get noise in one of the channels. Okay. So your problem is to try to deal with that and take the information from the channel that is carrying information and ignore the channel that is carrying noise. Okay, so this is like a more schematic representation of the problem. So you have here the original concept or the thing that you are perceiving, which is a cat. Okay. And then, yeah, you have the sound, you have the image, but then there is some mechanism that induces noise. So, and it's controlled by this gate. So, if the gate is in this position, this is going to become noise. So, there is no information here, so you have the information there. And if the gate is in this position, you get noise here, and you get here information. So your problem is you really don't know the position of this gate. What you receive is this, and then you have to make a decision and be able to solve your problem, which in this case is to classify between a cat and a dog. So what we did was we designed a unit to deal with that. This is called, we could call it gated multimodal unit. So basically, what this does is it's a neuron, you may think, a neural network model that is able to choose between the channels and actually to make a combination to say, okay, I will give like a 30% of attention to this and 70% to this, or in other cases, I will totally ignore this and concentrate totally on this, but the neuron is able to make that decision adaptively depending on the information that it's receiving, okay? This kind of designing like a neuron with this kind of behavior that controls the flow is something that was explored in the 90s. One of the typical applications of this is recurrent neural networks. There is one which is called LSTM, or yeah, LSTM is a classic one. So this was not a new idea. So what we were doing was like recycling some of those ideas. I mean, it's what many people are doing nowadays in deep learning, recycling ideas from the 90s. Okay, yeah, and actually, yeah, I'll show you something else that we recycled here. But yeah, we put that in a unit, and yeah, this is very typical of the kind of things that you have nowadays with neural networks. Okay, okay. So what was the idea? What were we expecting? So this would be like a typical example of a data set that comes from a similar example to of the cat and the dog, and the road with the multimodal perception. So you may have samples where you only have information, audio information, and you may have samples where you only have the image information. So this is like the visual modality. So here you have information about the cat and the dog, and this is just noise. And you have the text or the information, in this case, the audio information. Also, you may have when you have information, you may distinguish between the cat and the dog, but eventually you may have noise. So really you don't know in advance which channel is carrying the information. So the problem of the model is to learn where the information is and be able to solve the task. So this is very simple problem, but yeah, when you apply this type of unit to solve this problem, this sigma here, which is a neuron there making the decision between the modalities, actually learns to distinguish between the two cases where you have information in one channel, the visual channel, you have information in the audio channel. So this is this element here, and this is like the final decision of the unit that is able to discriminate between cat and dog independently of where the information comes from, the visual or the audio information. Okay, so this is a synthetic example of what we expect that unit to do, and the idea is to use as a building block for building neural networks. Okay, so there are like two main approaches to do data fusion. When you have different modalities, you have early fusion, which is this. You just concatenate the information. In this case, for instance, textual and visual information, and then you apply the prediction model. This is called early fusion. Or you can do late fusion. So actually, you have like a prediction model for text, a prediction model for the visual part, and then you have this unit here. This will be like an instance of late fusion. So actually, that's not a new idea. That's called a mixture of experts. So that was proposed in the 90s, 1991. And yeah, it's basically what we do in our unit, but here you have like experts. The experts are like classification models, and those classification models, I have to choose between the prediction of each of these models to produce the final prediction. The difference is that this is a unit that I can use in different ways. So what we are doing here is something which is called intermediate fusion. So what we did here was actually to propose a building block that allows you to do intermediate fusion in neural networks. Okay. So something which is interesting here is that you may have this like a layer where you do fusion and many layers, more layers here, and then you may have a model here for text processing and a model here for visual processing, a convolutional neural network, and then you can do end-to-end learning of the whole model. Okay. Okay. So yeah, this is like a generalization for many modalities, and these are three example tasks. One task is given a test, try to predict the genre. This is the description of a movie. So if I show you this, what do you think it is? What kind of movie? It's action, drama, sci-fi, animation? Action, maybe. No drama, right? Maybe sci-fi, animation, who knows, right? But if I show you the poster of the movie, yeah, definitely animation, sci-fi as well. Okay, so yeah, the problem was that to be able to predict the genre using the multimodal information. So this is a model similar to the intermediate fusion that we saw. We have many of these neurons, the GNU neurons. We have here a convolutional neural network for the poster, and we have a very simple model for the text. And yeah, what we show experimented, okay, and we built a data set with like 26,000 movies and posters. And what we show here is that, yeah, when you combine information, you get better prediction than when you have other forms of combining. Oh, yeah, actually, all of these are multimodal models. yeah, when you use tests or images alone, the performance is worse. All these are multimodal models, but yeah, ours works better, as expected in a table from a paper, right? Yeah, you always show, yeah, example where the model works better. But something which is interesting, right, is that using this unit here, right, you can see for which genre the model uses more the text information or the visual information. So for this genre, it uses text the most. For genres such as animation, as expected, visual information is more important. Okay, so this is interesting because and it's also interesting for musical. It's like half and half. Okay, for family, it's also more visual. So this is interesting because this gives some degree of interpretability to our model. We use also for image segmentation. So here the problem is doing the image segmentation, but we use two kind of sources or modalities. One is the RGB, the color information, but also the depth. Okay, it's with the depth camera. Okay, and then we have to classify 6 kinds of concepts: grass, obstacle, tree, vegetation, road. Okay, and yeah, what we did is a convolutional neural network for the RGB information, convolutional neural network for the depth information, and then we have a layer of GMUs, and then we have some the convolutions. Yeah, actually here we have the convolutions, and then the output of the model. Okay, and then yeah, again, what we show is that we get better results when we combine using the GMUs. We get better results for the prediction, and also we can look where for which concepts it gives like more importance to the RGB information, for instance, for grass, vegetation, and for other concepts such as sky or tree, the depth information is very important. And yeah, it's very intuitive why that's the case, right? Because sky is the thing that is farthest in an image. Okay. Okay. Also, we tried for a medical image analysis. So here, really, this is for a cancer diagnosis, for breast cancer diagnosis, and we have to basically, predict some if there are some tumor in some parts of the image. And the challenge here was that we have actually some features which are like hand engineered features, which is very typical in medical imaging. Okay, and then we wanted like to combine that with feature learn automatically using a convolutional neural network. Okay, so yeah, that's actually an interesting problem in medical imaging because more than in natural images, in medical images, the domain knowledge is very important, and traditionally domain knowledge was captured in the form of features, engineered features for detecting something. So that's something that you would like to use, and what we show here is when you use those kind of features, what you get combined obviously with convolutional neural networks, you get better results. So these are early fusion of visual information and the hand engineered features, and these are the fusion using GMUs, and you get better results. Okay? Okay, so this was published in 2017 in ICLEAR, which is like an international conference on learning representation, which is an important conference for people working on deep learning. It was okay. There are 2 tracks. But it was not published in the main track. It was like a workshop track. However, some people have already started to use it. This is a work from people in Facebook. These are actually already Facebook, like Thomas Mikolov. He's the inventor of Portubeg, which is very popular in tests. So what they did is they did a similar model. They used our model as a baseline, but also they extend the model. Yeah, this is really efficient. I mean, this is really large scale, millions and millions of data. They use, they also test, they work on our data set, okay? And what they show is that even though they are not able to beat the result that we got with the GMU, they got competitive results, but this is very, very efficient. Okay, so this will scale better. This is another example using. This is people using for also for medical imaging. Okay, so it's very similar to what we did for segmentation. They use at the last stage of convolutional neural network with two lines. And this is another example where they use this for generation of tests. Okay, in conversational systems, they use also the model for combining evidence. Okay, so it's interesting because it has been used. So this is basically I wanted to show. Thank you very much for the attention.
Thank you for your talk, Fabio, here. It was very interesting the way that you started because in some way we could say that our vision or our senses are balanced.
The signal is not really changing in sound, it's our vision that is changing the signal.
Right.
You want your systems to be biased in some way? Or what's...
Yeah, no, yeah, definitely. In machine learning, your system has to be biased. I mean, if you don't have, that's called the learning bias. If you don't have a bias, really learning is not a well-defined process. So yeah, there are some sort of bias, okay? I mean, that in general, in machine learning, so it's unavoidable. But for this particular case, yeah, you can think that when you have like an additional modality, you are introducing more information, but eventually more noise or a bias. Yeah, that's difficult to deal with.
So in some way you want to be closer to what a human will do. No
Yeah, but yeah. However, the advantage is in the okay. For instance, supervised learning task, you really have a very well defined goal, which is to be able to solve, for instance, a classification task with the highest accuracy, right? So if that bias is useful for improving your accuracy for your task, good, it's welcome, okay? However, in some cases, that's not necessarily good, okay? But yeah, bias is there, is unavoidable, and it could be a problem.
To merge multimodal information, you say like we either have to take the text, the language, and map it to images, or no, it's just an idea, or take the images and map it to some language, or maybe map either of those things to another space, rifle to whatever, in which we can interpret them in a proper way. Like, do you think there is any other approach to that?
Yeah, actually what you describe is like the traditional way to do it. You either map one modality to the other, or then you find like a common representation. However, what we are doing here is like finding like a common representation, but in a very localized way. So if your model finds a feature which is interesting, that comes from mixing the two modalities, that will be represented by one neuron. But your model may have neurons like this, the GNUs, that mix the information in different places. So it's really distributed. So what I would say that the advantage of this is that you can do all of them like at the same time, and really the model is going to learn what was better, right? Like finding a common representation or mapping one to the other, right? So yeah, here there is not like a previous commitment on what way you want to represent information. The model learning.
But do you think there is like another approach instead of mapping?
No, no. I mean, the mapping to having a common representation. That's very general. I mean, probably any other way that you want to where you deal with this kind of information, always you have like some representation there, some implicit representation. Yeah, I would say in general what you're looking for is for different representations. Yeah, but you not necessarily have to mix them at the beginning. You can mix them in an intermediate step, and that's what happens with this kind of model.
I have a couple of questions. But this is a multimodal deep learning. The models that you built, or the time for training time that is spent to train this kind of model was huge against to the train a model only for visualization task or audio task. So that's the first question. The time was huge. It was more expensive to train a model, this kind of model, against all the other.
Yeah, that's like a common problem to deep learning. Training time is usually large when you have a large model and large data sets. So it could be the order of several hours, sometimes days. Yeah, but that's common nowadays. So, however, the advantage of formulating a model using this kind of approach, I mean, even if your model is not neural network based, many models, machine learning models, can be formulated at they were neural networks. And there is a huge advantage of doing that nowadays because there are very good frameworks that train neural networks in a very, very efficient way. So, yeah, the answer is yes, this is expensive, but we can take advantage of TensorFlow, PyTorch, or other frameworks which are very efficient for training that kind of models. Okay?
The second question is about the inference time. So the inference times of these models are even more expensive than taking the models using exclusive only image.
Okay. Yeah, it could be some overhead. We are not really thinking about that. I mean, we are not addressing in particular that problem. However, because actually there are people working on that. Okay, so for instance, you may have heard of neural chips for smartphones. Huawei has some chip that I don't remember how they call it, but that's going to be very common. I mean, not in the future, right now. So inference time for this kind of model, for neural network models, is going to go down. So even if it is costly now, it is not going to be in 1 or 2 years. So yeah, that's not our concern.
Okay, thank you, Fabio.
Okay, thank you very much. Gracias. Gracias. Ya que lo tenía ahí,
I now Pablo Arbolais will give us the second talk about the machine learning and vision issues. Correct the title. I need before you ready.
Y vamos a tener listo. Vale, antes de parar acá y si haces tu que sea listo.
Ok, ¿en cuál? En este de acá.
Está aquí a la izquierda.
¿Listo?
Sin micrófono. Y
Just
si quieres
after
cambiar,
the talk of
si quieres
Pablo,
al final me la puedes enviar esto para yo
the
compartirlo
break is
Va a
organized
estar más difícil porque tengo
downstairs in
bastantes
the
resultados no publicados.
basement one.
Entonces, sí, luego me pasas una.
You will find the
Dile aquí.
poster session is the main dish. And
Yo estoy compartiendo
That's
esto
all
con
you
nuestro
don't
invitado.
copy,
Sí, sí,
¿No quieres que lo
no, no, está bien, yo te vi ahí tu charla desde mi oficina.
wow,
I thought it was about video, no?
more or less, more or less. Okay, thank you, Pablo.
Okay, hello everyone. Thank you very much, Tiberio, for the invitation. So, let's see, does that work? Okay, so today, instead of giving you an overview of the work we're doing in my group, I'm going to talk in more detail about two projects. And the common thing on those is the use of video and of temporal information. So, this is the first project, and I'm very happy that Fabio came before me because he already discussed the essentials about deep learning, so I won't have to cover that. So the first problem is video object segmentation, and this is work of my students Maria Alejandra Bravo and Juan Carlos León. So what is this about? So we're studying the problem of segmentation, right? Segmentation is like the holy grail of computer vision. One would like to have regions in the image, and ideally those regions should correspond to objects. And why do we want to do that? Because we could then reason in terms of those objects, not anymore in terms of pixels, but really in terms of higher level entities that will allow us to have a deeper understanding of the image or of the video in this case. So this is the data set in which we're working on. So you have two formulations for this problem in the case of static images. Either you have image parsing, in which you want to segment every region in the image, or you have semantic segmentation, in which you focus on a particular set of categories. You want, for instance, segment cars or segment people, etc. The framework we're using here is slightly different, because what we want here is to be able to follow an object or a set of objects throughout the video, regardless of their semantic category. So what we will do here, the setup we have is, we have a video sequence, and then in the first frame, someone marked what he wants to track. And our goal is to track those objects throughout the video. So these are some of the annotations of the data set that we're using, and you can see that these are very general videos. Complex scenes with a lot of very general types of scenarios. So what is the game here? So on the one hand, we have the static image information, color, texture, shape, and on the other hand, we have the motion information. We have optical flow. In the case of stereo, we have disparity, and the goal is, of course, to merge those sources of information. This is a kind of multimodality, but within okay, so these are the two versions of the tasks we study. So this is the sequence, and then, as I told you, we only have information for the first frame. So the first version of this problem is to have one single mask in the first frame, and that mask can have several objects. Here, you have one mask for all the wagons, and the idea is to follow them as one single object. The second version of the problem is to consider multiple independent objects. So here, each wagon is a different object, and you have to track them independently. And again, we only have the information on the first frame, and the goal is to propagate that information to the complete video. How do we evaluate this? Well, in the same way we evaluate segmentation in static images, we use what's called the intersection or union score, or the Jaccard index. It's a very simple metric. You have your annotation, you have your prediction, and then you compare them pixel by pixel, and you divide the number of pixels in the intersection, the true positives, by the number of pixels in the union of the two masks. So this metric combines the two types of errors one may have in a classification problem. It is a number between 0 and 1, and of course we want to get 1, which is a perfect match with the annotation of 1 point. So there is a lot of related work in this area. This is a very hot topic in the field. I won't discuss the details about the related work, but something that is common to all the approaches is to have a two-stage training. So what does this mean? So we have a training data set, and in that data set we have many videos, and for each video we have all the frames annotated. So we can train some system that is generic and then just predicts some segmentation for a given frame. And then we also have the information in the first frame of the test video. So we can take that generic system and specialize it for each of the objects we will see in the different videos. I will describe this in more detail in a few minutes. So this is our approach. This has a lot of boxes. I will explain this in more detail. As I said, well, what's important here is that we're following this kind of general strategy of first having a generic model and then specializing it for the first frame of each test video. We're using as loss function the objective to guide our result, the dice coefficient, which is nicely related to our final metric. Okay, so, and the goal here is to really understand how to combine these sources of information, like Fabio was doing, but instead of text and images, here we will have motion and color, for instance. So the first take is to use the color information, and in that case, have an image and you want to obtain the mask. So what all these colored boxes mean is the architecture of the network. So in the first part of the network, one has a traditional classification architecture in which you get the image and then do convolutions with filters. You reduce the spatial dimensions and increase the number of filters. The effect of that is that as you go deeper in the network, you have more and more access to bigger parts of the image, and also you have access to more high-level information. So the first filters, as Fabio was showing a few minutes ago, detect things like edges and blocks, and as you go down, then you start getting things like limbs or faces or parts of objects. So this is the first part, and then this is what's called an encoder, and the second part is called a decoder, in which we take this information, which is very coarse spatially, and then upsample it in order to get a result which is of the same size of the original image. And in doing that, we do something which is called skip connections, which is taking the features that we had in the encoder and feeding them back in the decoder in order to obtain better details in the results. So that's the overall architecture. We're also using a recent technique called dilated convolutions, which what it does is in traditional convolutions, you look at a patch of pixels. In a dilated convolution, you do the same, but those pixels don't have to be contiguous. They can be separated in the image. That way, with few parameters, you can look at bigger patches of the image. That's very nice, and that gives you a lot of contextual information. And that's precisely what we were trying in those experiments. I will only talk about the Jacquard index, the F1 measure is equivalent. So this is our basic network, 0.53. I remind you that we want to get 1, so this is half working. And then as we add these dilated convolutions in this part of the architecture, the result improves significantly. We're having access to more context information. If we do that in the second part, we also improve with respect to the baseline. And finally, of course, if we include the dilations in the whole architecture, we get a result which is better. Okay, the second source of information is the optical flow. So the optical flow tells you for each pixel in the image where it will move in the next frame. Okay, this is a visualization for the optical flow, and here color means direction. So this means the horse is moving in that direction. And the intensity here is related to the magnitude of the motion.
the saturation, sorry. So, so we have this additional information. We can compute this with a separate neural network. The question is, how do we combine color and motion? What is the most appropriate way of merging information here? So we did all the experiments. As Fabio said, we can have early merging. We can combine them just in the entrance of the network. We can have two completely different networks and then combine the results in the end. What we found to work best in this setup is a kind of intermediate network, intermediate fusion, sorry, in which we have a first part which is independent for the two types of information, and then we merge them in the later parts of the encoder. What this means is that the type of features that are complementary are very low level, right? So once we only need them to be separate for the first stages of the network. Afterwards, we can combine them. And these are the results, of course, trying to feed in this new information in all the parts of the network. And you can see that basically this is all very similar. That doesn't make a big difference. But there is a difference in terms of number of parameters. So, of course, we choose a conservative setting in terms of number of parameters in order to avoid overfitting. So we want to have as few parameters as possible because our training data is limited. Okay, and then the third component in our system is the segmentation history, we call that, which is our result in the previous frames. Of course, if I have a result now, and then the next frame, the result in the next frame must be very similar to the previous one, especially if I have 30 frames per second. So we want to use that information. So we combine our results in the previous frames into a new image, and we do the same experiment. We try to combine color and this segmentation history in multiple parts of the network. These are, again, the results of the experiments, and coincidentally, we see that more or less the same level in the network is appropriate for merging this type of information. That was the same for the optical flow. Okay, so this is the final system in which we integrate these three sources of information. And these are the results. So here is an additional experiment which is working. You can use the optical flow to move the mask to the next frame, and then use that moved mask for your inference. That gives a small improvement in the results, but they are very similar. Okay. So this is our architecture. How do we train it? So as I said, we have our training set with all the frames annotated. We train a generic system there that will just take some color information, motion information, and segmentation history and produce a mask. Then when we get to the test set, we have the first frame annotated, and we continue training our system only using this image. We do what's called fine-tuning in this area, which is to continue the learning, but with a very small learning rate. We just modify a little bit our original parameters in order to adapt them better to this specific sequence. Okay, and these are the results. So these are the overall results. And so you can observe the improvement by adding the information with respect to color only. So by adding optical flow, we jump maybe 10 points. By adding the segmentation history, we have a smaller improvement, but it's also meaningful. And finally, by combining the three sources of information, we get a bigger boost. So we go from 66 to 77 with the three types of information, which is quite significant. And it was just the generic network. So if we, in addition, specialize the results for each of the sequences, or for the first frame of each of the sequences in the test set, we get an improved result. However, we can see that we're hitting here diminishing returns, right? So the improvement by adding the sources of information is much bigger than the one by training in each specific data, but still it helps. So here are some qualitative results. I won't spend much time on that. But what they show is that indeed the different sources are complementary. So let's take an example. So here are two camels, but we only want to segment this one, and it's moving. The other one is not moving, or it's moving very little. So you can see that with RGB, we segment them both. With optical flow, we focus on the moving camel, but we lose some details. And finally, well, with our final system, we can record from those mistakes. So we're able to combine effectively the different sources of information. Okay, so here is the comparison against the state of the art. So here are our numbers. They are competitive, they are not the best. I will explain a little bit this product table. So a family of methods that obtain better performance than ours use semantic information. What does that mean? So they run a person detector. So of course that helps because many of the videos we have people on them. However, that makes the system less general because if you don't have a person, then your system will fail. So we didn't use that kind of information to preserve the spirit of the task. We want to be able to track any object across the sequence. There are two other methods that make use of a lot of data, additional data, in particular Microsoft token, which is a huge data set, and of course that gives them an edge in the results. And finally, since this was a challenge, all these methods use a post-processing technique, which is either a conditional random field or heuristics like selecting only a connected component that overlaps most with my previous result. Those are little tricks that can help and can help a lot. So you can see this method, which is the winner. So without the post-processing, they get maybe 1.5 points above us, but with the post-processing, they get a significant improvement. Okay, where are we? Okay. Of course, we can also add post-processing and additional data. The idea here, as I told you, was more to understand how to combine these tools that we want to challenge. Okay, and now we're working on the second version of the problem, which is tracking multiple objects, segmenting multiple objects simultaneously. There is a new version of the dataset, which is bigger and more diverse. And our initial approach here has been a direct extension of what we had. So previously we had for one mask, we can track it. Okay, so here we have 4 masks, so we track each of them independently, and then we merge the results. That's a direct extension of what we had. However, you can observe that the results, the numbers are much lower. In the other problem, we had like 80%. Here it drops below 50 or even 30%. This is a much harder problem. And here is the reason. So this is one of the examples, and we want to track the person and the 2 dogs. And of course, the difficulty here is that, for instance, this guy leaves the scene for a while and then comes back. So when the dog comes back, we have confused it with the other one. We lose the identity of objects that are outside of the frame, and also the motion is quite challenging. So the dog is jumping in front of its owner. That makes the identities of the pixels to get mixed up. And that can be seen in the results. So this is the performance across frames for person. We track the person very well across the video. One of the dogs goes down, and the other one just disappears, and once it disappears and comes back, we never recover it. So that's a limitation of our algorithm. We're only considering temporal information in short temporal videos. Here is another example. So these young ladies, the video is just zooming in. So the appearance changes drastically from the first frame to the last one. Here we couldn't see their faces. In the end, the frame is only their faces. So that causes a lot of problems for our method. Of course, we have issues updating our appearance model. So that's another limitation of our approach. We need stronger appearance models. And here again, you can see that we start very well, but as appearance changes in the video, our results degrade until they get basically garbage, as you can see here. Here are some interesting things. Turns out that these girls had some cell phones. So you also have to track the cell phones. Of course, this is completely lost in our page. Okay, so what are we doing? Of course, we're using bigger architectures, larger networks. That already helps. So let me put that maybe in context of the new challenge. So these are our current results. These are the best results, so we are not too far from them. And in these results, we're only using color and the segmentation. We're not yet using optical flow, so we hope that we will get to the points that are still missing by that information. Okay, but what's really missing here is, as I said, some long-term analysis. So we need to think of the video as a whole, and if the log goes out and comes back, we need to identify that same log. And well, on the other hand, these methods are very greedy on data. We have like 100 videos. This is nothing for these methods. There is a new data set which has 4,000 videos, which is an order of magnitude more data, and we are eager to start playing with it. Okay, so what did we learn here? So the three cues we analyzed, color, motion, and segmentation history are important. They are complementary. And in order to improve, we need more long-term analysis, and also we need additional training data. So these are some results of this method, the original ground truth on top, and our results on bottom. So I don't know if I should take questions on this project now or wait until the end. As you wish. Does anyone have a question?
How much frames per second are running the video?
Yes, so this is not real time. However, let me see. Maybe 10 frames? 10 frames per second with our current hardware. This is just a matter of hardware, right? You get more GPUs, you get faster. So inference is not a big deal here. Training time is consistent, so you need several days, but inference, this hardware is optimized for it, so it runs very well. Any other question about this?
How do you use it for optical flow?
For optical flow, so we're using a method based on deep learning, which is called FlowNet 2. It's like the latest version of optical flow, and it works really well. The advantage is that it also runs on GPU, so you can have your results.
And it goes like one frame to the next one, consider more frames.
No, 2 frames, 2 consecutive frames. You can also run it in more and then aggregate the optical flow, but the standard thing is 2. Other questions?
Maybe it's not related, but last week or 2 weeks ago, they presented the conference from Apple, the new version of ARKit, which is an API for augmented reality. And what they are doing is object tracking in real time. That type of algorithms, what kind of things can we get from those algorithms that are useful for yours?
Oh no, so this is very related to tracking, right? So here we want to track every pixel you wish of the object. So usually tracking algorithms can be an input to this video segmentation work. In particular, we have you can have point trajectories, which is tracking points across the whole video, and that gives you a very strong signal for time consistency across the whole video. So yes, you can use tracking for this problem. The other way around is a little harder, I would say, but they are very likely. More questions? Okay, so let me jump to the second work. So this is about automated facial expression understanding. This is the PhD project of my student Andres Felipe Romero, and this is in collaboration with my other PhD student, Juan Carlos León. So this project has been financed by Google in the last 3 years. So, facial expressions. They are, of course, paramount to us. They are the most important form of nonverbal communication, right? When we want to discuss something serious, we say, let's do it face to face, right? That brings us a lot of information to understand the art. So that has been a subject of study for a long time in psychology. There is a researcher called Paul Ekman, which is very famous here, and he did this study in several ethnic groups across the globe, and what he found is the following. So that's very natural seen from today. So we all have, so facial expressions are caused by the contraction of the face muscles, and we all have the same muscles. So if we study facial expressions in terms of the contraction of those muscles, then we may be able to understand all facial expressions. So those are like the atoms of facial expressions. So what do they mean? These are what's called the micro-expressions, or he called them action units. So what's a micro-expression? Outer brow riser, when I do this, right? This is just a single muscle that is contracted. So he identified all these action units. He coded like around 40. And then he created a dictionary of action units. And psychologists get trained to recognize them. So you need a training of about 2 years to be able to spot those in real time in a video. Okay? And as I said, the interesting thing about working at this level is that these are the essential units of facial expression analysis. When you think of someone happy, well, being happy is just closing your eyes and pulling your lips. That's a combination of 3 different action units. And when you are disgusted, that's a combination of 3 or different action units. So by focusing at this level, you can have things like happily disgusted, which is the union of happy and disgusted. And not only that, you have your door open to any applications, right? So if you want to detect, I don't know, intoxication, so you may, or lies, you may have some action units that are activated when a person is lying. So this is really the key to this field, to be able to work not only at the level of global emotions, but at the level of micro-expressions. So what's the issue? Well, the issue is that there are many of them, like 40 of them, and they are activated at the same time. You can have multiple of them at the same time, and you can have some of them that are incompatible. So, and all this needs to be manually annotated. So psychologists in a room doing this, it can take them many hours to annotate just 1 or 2 minutes of video. Yeah, well, so where do we study this? You can see much, but there is a database. The biggest one in this field is called PP4D, and the characteristic of this data set is that the emotions are spontaneous. So they try to elicit the emotions instead of telling people, laugh, they just told them a joke. So the emotions are more natural, which makes the data better. Still, this is a kind of restricted setup. You can see that the background is always the same. These are young people from some university in the US. But still, well, we do have data to work in this problem in a quantitative way. Okay, so here is an example. Among the 40, we only use the 12 which are more common. You can see them here. And here is an example. In this frame, those action units are active and the other ones are not. For instance, I don't know, 2 outer brow raisers. So this guy is raising the outer part of the brows. So you have another frame, and the difference between this one and this one is that. So lip pressure, okay, what we call here hacer cara de foco. That's what he's doing from this frame to this frame. But this is very subtle, and then you can see from this one to this one, he moves, but the action units don't change. So this is a very subtle and localized problem, right? In order to determine if this thing is moving, you don't need to look here. As a consequence, the dominant approach for this problem has been based on key point detection.
Has been based on key point detection.
Thank you. So, what does this mean? Okay, so we take the face and first we detect key points. What are the key points? So all the parts of the face. And then we can use that information either to align all the faces or to select patches around those key points. So now you will be looking just at the corner of the left eye. And if you can detect those points reliably, so you will always be looking at the same part of the image. The issue is when your key point detector fails, right? Then you will be looking to another part of the face and thinking that's the corner of the left eye. So this has been the dominant approach. Align everything and then reason locally. Our aim here was, again, to consider multiple sources of information because a face is not a patch of pixels. A face is a three-dimensional surface that is evolving in time. So we would like to use that additional information, like in the other project, to model better these changes in action unit activation. So let's start with the RGB information. And our question here was, do we really need to do this intermediate step? Can we just put a face in and then say if the guy is lifting the outer row or not? That was the experiment we did, and the answer is yes, we can. So here is the image. This is a network that was originally trained for image classification that we specialized for the binary task of saying, is this action unit present or not? And we do that not for one of them, but iteratively for all of them. So in the end, what we have is an architecture that has a shared representation for all action units, and that has specialized heads or classifiers for each of them. That's economical. This doesn't use a lot of RAM memory in your GPU, and it's also fast because with one single pass, without any key point detection, you can get the activations of all the action units. So that works well. However, we are sacrificing performance for efficiency. This shared representation is elegant. However, one may think that if we have a specialized representation for each action unit, we may get better results. That was our next system. And what we did here was to train a whole network for each one of these action units. And of course, it works better. So these are the results. This was the best method at the time. In this data set, this is average precision. No, this is the F1 score, the F measure, the harmonic mean of precision or recall on a threefold truth validation. That's the metric in this data set. This was the best method at the time, and these are the two versions of our system. So you can see that just by doing this holistic analysis, we obtain we don't obtain any improvement. I think this is wrong. We obtain a small improvement with respect to this one, but when we train independently each of the action units, we get a better result. Okay, so the next question is to understand if we are really focusing on the right information. Because a criticism reviewers made was that they didn't really know if we were using the right information or not for detecting it. So with these visualizations in which we color the pixels depending on how much importance they have to make the decision, and indeed, for the outer brow razor, we are focusing on the eye regions, and for the action units related to the mouth, we are focusing on the mouth region. So the network is learning automatically to focus on the right region of the face. Yeah, well, so that information, time information, again, we make use of the optical flow, and here it's also very relevant. So you can see here an example. The changes in color are very subtle. She's opening her mouth here. However, the changes in motion are much bigger, right? all this part of the face is moving down. So we may hope that this additional information will be useful to classify the action units. So we tried several variants of combination. I won't go in length on them. This was the type of variant that we had in the previous project, in which we have the initial part of the network independently for each feature, and then we combine it. We can also have late or early fusion. We can also have only the optical flow and see if only the motion information is useful for classifying the action units, or we can, in an early fusion stage, do concatenate as additional channels or as an additional image the optical flow. So we tried them all, we evaluated them all, and the best setup in this particular problem is this one. So we are using the optical flow as another image. So the hypothesis of why this type of approach is working here is because of the changes I was showing you. You have really a visual signature localized when some action unit is activated. Okay, so optical flow gives us a couple of points, which is good. And finally, the depth information. So a limitation of this data set is that all the faces are frontal, of course. So last year, the creators of that data set made a challenge called the FAIR challenge, facial expression recognition and analysis, I think. And the characteristic of this is that they they rendered the faces they had already acquired from different points of view. So here you have 9 different points of view, and you have to detect all the action units in each point of view, and you don't know which point of view the video was taken from. So here you have another example. Another example. So this data is kind of funny, right? So you see that there are some artifacts in the face because it was rendered, and that the background is funny, but still it gives us access to a much larger data set. Okay, so this was the system we implemented there. I'm putting more time. Okay. I'm almost done. So we had initially, so first we need to know the view of the video. For that we had a classifier which told us from which view it was taken. And then once we had chosen the view, we run our previous method using color, depth, and optical flow. Finally, since the predictions were done independently in each frame, we had a temporal consistency stage in which we smoothed the predictions across time. Okay, so this is the final result in the challenge. The baseline of the challenge was at 43. You can see that this is a more challenging setup because we changed the views, and we obtained 57%, which was the best result last year in the challenge. Okay, so what are we doing now? The great limitation in this field is the annotations, getting the annotations, right? You have to train, yes, I'm almost done. You have to train a psychologist, and then you have to put him in a room to annotate. So that's not scalable. So what can we do? What we're trying to do now is to generate images with particular expressions. In order to do that, we're using a very successful framework called generative adversarial networks. This is the simplest version of these networks. So what we have is a couple of networks which play kind of a game, a generator which produces images, and the goal is to fake the images from a real data set, and a discriminator which has to determine if the image that it's presented with is real or fake. So of course, in the beginning, the generator generates garbage, and the discriminator has a very easy task. And then as the generator improves, the task gets harder, this guy gets better, this one better, and in the end, you can just extract the generator and produce images that are very similar to the ones in your database. So that's like the holy grail in this area. If you can generate automatically your training data, you're done. You have infinite amount of training data, and you can just let your GPUs train and obtain better results. This is unfortunately not an easy task. So we have been trying to do this, and we are not the only ones, of course. In all the problems of computer vision, people are trying to do similar things. So here are all results. So these are all generated faces, and they are generated with two different action units, the outer brow raiser, and this is the lip corner puller. So this person here should be smiling, and if you look from that distance, they look kind of smiling. When you look from this distance, you start to notice the artifacts. So this is where we are now. So the images look reasonable. However, they're not yet good enough that you can use them as additional data to improve your classifier. We train with these images, and we don't get an improvement on real images. So that's the real challenge, and not only for this problem. It's really a community-wide issue, how to generate automatically data in order to train these larger models. So this is all. Thank you very much. I'm missing the most important slide. Of course, this is not my work. I'm just here presenting it. This is my group, and the work I presented today was the master thesis of Maria Alejandra, who is sitting there, and the PhD project of Andres Felipe, who should be sitting there, in collaboration with Juan Carlos, who works on the optical flow. So thank you very much, and we'll be happy to answer questions.
Question?
Yes, so for the one where you were generating images for testing the different characteristics of the face, have you considered, instead of generating the full face from scratch, rather using like video games, different 3D models, and then like using the generative networks, not to generate the face, but instead to do the job of the animator? Like, because in there, we already, like, that's what animators do with their creative videos. So that way, maybe you could reduce some of the artifacts.
Yes, that's true. So, yes, of course, here the connections with graphics are evident, and people have been trying to use synthetic data for a long time. So it depends on the problems. For instance, optical flow, precisely. I was talking about optical flow. Getting annotations for optical flow is impossible. How would you know the motion of each pixel? So for that problem, the datasets are synthetic, and you render, there's one of flying chairs. Okay, it's not very realistic, but the motions are, and you can train methods that work. That has worked for optical flow, but not for many other problems. So these models are very expressive. So they can very well determine some artifact in your data and then hang on to that and use it to classify it. So yes, even if you don't see the artifacts, if there are some, the network will catch them.
Images indicated automatically. How consider label? There are automatically labeled.
Oh yes, so I didn't talk in detail about that part, but of course, what we want is to input the system with a neutral face, and then be able to activate any of the action units. So for that, we need to show it examples of the action units activated and not activated.
Not going to some kind of error or not, because you are generating a new image, you are labeling as mine, but you see the image and it's right, no. So that's my question.
Yes, so precisely. So the real test here is not that they look nice, but that when you train with them, you actually improve your real data. So yes, if your generator is bad and you generate things that don't look like faces or that have the wrong expression, so it will just confuse your classifier.
So, but it says it must be on a supervised learning, right? So the image is generated, I must verify that.
This is supervised. This is supervised. So we're using the labels and we're inputting neutral faces and faces with action needs activated, and we want to teach it to turn them on and off.
We want to verify each image time that is correctly labeled.
Yes. So to train that, we are using our database, which was already annotated. Any other questions?
Thank you very much, Pablo. I pray you 4 minutes of your precious time to take a picture, a global picture of all of the group under the dictature of our photograph. En la terraza. De terraza. And go down to basement 1.